And we're back. In this video, we're looking at how can exponential functions appear in a table of values and graphically. And then from there, we're going to look at how can we actually apply transformations to an exponential function. So let's say we have a table of values right here. And notice we have two different functions. We're going to examine each of them separately. So we look at this, and what we're going to be looking for, what we're going to notice, is that with every x value, there's going to be a common multiplicative factor. So what we're saying here is I can multiply 5/9 by something to get 5/3, multiplied by the same thing, by the same thing, by the same thing each time down. So you can kind of relate it to slope in a linear function, but we're more of multiplying here. So to get from 5/9 to 5/3, we had to multiply by 3. To get from 5/3 to 5, again, we're multiplying by 3. And it's easier to see with the next set. 5 to 15, multiply by 3, and we multiply by 3. So a common multiplicative factor, this shows us it is a exponential function. And looking over here, going from -2 to -10, we're multiplying by 5. -10 to -50, multiply by 5, by 5, and by 5. So again, a common multiplicative factor, resulting this being an exponential function. So what would their functions be? How would we actually write their functions? Well, we know an exponential function requires an initial value a and the factor b raised to the power of x. So we can get that from each of these, from each table here. Look, and our initial value is when x is 0. So when x is 0, our first function yields 5. And then the multiplicative factor is b, which is 3. That would be the function for f of x. So what would the function be for g of x? You're thinking about this, and you're noticing the initial value for g of x is -50. So we would have -50 with a factor of 5. So there we have the function for g of x. And that's exactly what we're looking for in a table of values. It's just a common multiplicative factor and then what the initial values are for each function, and that's it. So graphically, what we can say here is we can kind of use this is with a function, we know the y-intercept will be our value of a. And then when x is 1, we know, so think of 1 here, we're getting 1 comma b. Now I'm going to add, for this graph, for simplicity's sake, we actually are examining it when a is 1. So when a is something other than 1, and it does change slightly, but not much. So back to this, with the 2 points, we are able to draw our graph. And this is not new. We have been seeing exponential functions for quite a while now. I just wanted to review this again. So this is where b is greater than 1. What if b is between 0 and 1? So we're examining like 1/3, 3/4, 1/2. What do we see here? So again, our y-intercept is still the value of a. And then we see that our function is decreasing. So what we can say about an exponential function, we saw this earlier, the domain is all real numbers. Because there are no vertical asymptotes. And then with the range of our functions, the basic function with no other terms being added or subtracted, our range goes from 0, not including it, to positive infinity. So we could say based off of that we have a horizontal asymptote at y equals 0. So that's just the basic understanding of the graph. All exponential functions will have this appearance, but there's going to be some slight changes based off what numbers and other additions we have. So let's look real quick at transformations. So let's say we have, so again we're focusing on transformations. Of our basic function. So let's say we're focusing on just the generic exponential function 2 to the power of x. So I can apply all of these transformations to any exponential function. We're just looking at 2 to the power of x. So let's say we have a function g of x, and we have 2 to the power of x minus 6. So these transformations are still the same from when we looked at quadratics and when we looked at rational functions. We see that we have subtracted 6 from the inside of our function. So I could technically write this as f of x minus 6, technically, because I placed x minus 6 in. So we would say that we have shifted f of x 6 units to the right. Okay? And let's examine another. So let's say we have m of x, 2/5 multiplied by 2 to the power of x plus 1. So very similar to the previous. We are having some sort of horizontal shift, but we see that we have a factor in the front. Again, so we're multiplying by this. So we see, again, we have a vertical, like always, a vertical stretch of some sort. So let's write this down. So we shift f of x 1 unit to the left and have a vertical stretch by a factor of 2/5. And there are ways you can write that a lot shorter than I did. It's just how I chose to write it down for this problem. And to end this video, again, another short video. Let's say we have this function h of x 2 to the power of negative x. And you might want to say that the negative x results in a reflection over the x-axis. I want you to be careful. It is a reflection, but I would actually rewrite this in terms of f of x. This would be f of negative x. So I'm placing the negative on the inside. So we haven't seen this in a while. 2 to the power of negative x. This is actually a reflection over the y-axis. So you might ask, what would it look like if I'm reflecting over the x-axis? So what would a function look like if I'm reflecting over the x-axis? So think about that question. Any concerns you have, any comments you have, please post them in Google Classroom and we'll try to answer those questions before you come into class. See you then.